So good morning and good afternoon, ladies and gentlemen. I think the main theme would be to share with you the findings from the SIGRE working group on multi-frequency stability of converter-based modern power systems, and that basically is the working group that has been sort of harmonized or in continuous dialogue with promotion, basically during the entire sort of working group sort of duration. Let's and my name is Łukasz Kocewiak, and I'm from Ørsted Offshore. So within this presentation, I would say briefly touch upon about the analysis methods to be accommodated for stability aspects, mitigation methods, initial proposal of the analysis flowchart, an example basically how the discussed methods could be applied, and at the end of the day briefly about validation procedure and of course other relevant working groups, as this topic is quite sort of I would say heavily explored within sort of entire industry. So maybe just jumping directly, which of the sort of multi-frequency stability analysis methods in let's say modern power electronic based power systems are taken into consideration? So as you can see, the majority is related to frequency domain stability methods such as transfer function based or impedance based or passivity based, where we are able to represent the system as obviously or different, let's say, components of the system as black box models, which would allow us to exchange information among different industry shareholders. And we can see here that tiny differences between different methods. So transfer function based, it is very much from classical approach used in control theory, where basically robustness can be quantified and stability indices can be defined. However, there are some challenges with respect to basically root cause analysis. Very similar is with impedance based, which is quite how to say useful to determine whether the stability is assured or actually there are some risk of instability, at least with respect to linearized system investigation. It has been taken from DC grids at some point of time, and right now is, I think, extensively used in both DC and AC grids. What is maybe the most challenging part is that within this method, it is difficult actually to quantify the robustness, as the sort of impedance profile might change from busbar to busbar. And of course, it's not that useful for root cause analysis. Passivity-based one, commonly used in traction railway systems, takes also very similar approach as one would say impedance based, or it could be a branch of impedance based, where it is also difficult to quantify the robustness. However, there are sort of more, I would say, sophisticated methods that we basically take into consideration, which is eigenvalue based, where still black box model can be integrated. However, there is an opportunity to build the state space representation of the entire system. Therefore, it has been used, I would say, quite extensively for power system stability studies, especially within a lower frequency range when some kind of electromechanical modes might be investigated. And the advantage here is that, of course,
there is a sorry to interrupt you. There was a small wish that you minimize the black box that you have there to the right. Thank you. Sorry.
Yes. Thank you very much, Paul. And within this method, we are able to actually provide some kind of quantification of robustness, and what is even more important, to provide analysis defining the root cause of potential instability, and that it seems to be quite how to say beneficial with respect to sort of multi-vendor, multi-frequency, and quite sort of extensive complex power systems. And of course, here, the last one defined as time domain, meaning that basically there is a system representation with nonlinear components that could be used basically for validation of a frequency domain outcome, but also looking into sort of the stability investigation within the wider area, so actually outside the linear system representation. We try to propose how specific analysis methods could be applied depending on the sort of asset life cycle phase. So here, maybe it's more simplified than the one shown in the previous presentation. However, quite, I would say, representative for this sort of particular discussion. So we have initial design, we have digital design phase, we have something related with commissioning, and obviously operation at some point of time. And depending on that phase, different methods could be more supportive, and some of them maybe might not be needed, depending on the sort of level of details to be investigated on different phases, and of course level of complexity. So what we can see here is that impedance-based, due to its quite sort of straightforward approach, so meaning that the impedance could be even reflected as a lookup table, it could be even done at the very early phase of the sort of asset life cycle. When we go to the detailed design, one can see that all of the methods could be equally utilized and used for investigation. What is maybe worth to mention that impedance-based, it is just fine to identify whether there are sort of instability challenges. However, eigenvalue-based stability analysis perhaps is more useful in order to investigate the system in detail in case of instability, determine the root cause, and have a quite clear indication what are the potential mitigation measures. During the commissioning, we start to use sort of less the frequency domain approach and basically support with time domain when sort of potential maybe retuning of the system is needed. In operations, quite popular is time domain approach. However, for instance, impedance-based also could be useful if there is a need of checking the stability on the sort of particular location of the sort of multi-busbar entire power system. Eigenvalue based, yes. However, maybe there's a challenge with respect to complexity. So therefore, it is at least not seen that it is that commonly used. And on the next slide, when we sort of know and we have the overview about different analysis methods, then we can, of course, look into mitigation solutions. Where also in the same way, depending on the asset life cycle phase, we could determine, let's say, those four representative mitigation methods. So one very simple, the first one related to control parameters tuning. The another one is actually with related with changes of the operational scenarios, topology changes of the system. The third one regarding some kind of hardware reinforcement on the power system level by means of passive filtering to improve the damping, and of course active reinforcement of the damping in the system. And of course, this is, I believe, quite intuitive, but the most I would say how to say less aggressive way of handling the instability is basically changing the controller parameters. So therefore, it is quite sort of preferred way of moving forward. However, sometimes maybe insufficient. and therefore there are other aspects like additional, for instance, active damping, which might require some extra hardware, how to say, sizing or enforcement in order to actually accommodate that functionality. Sometimes it also could be considered as an additional device that could be applied either in the design phase or as a mitigation measure during the operations. Passive filters obviously relevant for detailed design because there is a need of actually having quite a lot of information about the system and hopefully to make the robust design. It is also used in case of operation of the system in order to sort of improve the damping in the assets if there are some potential changes. In operational scenarios, this is not typically used that much in the design. I think to be avoided, the design can be considered as robust when actually operational changes or let's say exclusion of operational scenarios is avoided. However, during the operation itself, that is quite effective ad hoc solution. Here is the proposal of quite simple flowchart. What are sort of the main steps in order to assure the multi-frequency stability of converter-based power systems? So definitely small signal frequency domain approach at the very beginning, because it would allow in quite sort of effective manner to screen sort of the almost entire, even if not entire range of different scenarios by means of sensitivity studies, by means of topology changes, and have a quite good sort of map or landscape of potential instability places. However, frequency domain, we know it is representation, linear representation of the system. Therefore, validation in time domain, when the sort of nonlinear model representation is used, is very sort of crucial to be sure that actually the linear assumptions are just fine for specific operating conditions. And then, of course, we could have from small signal stability perspective pass-fail criteria, whether the system is stable or not, and whether the sort of instability mitigation method, one of the presented in the previous slide, to be applied. And if the system is fine, then we need to go beyond the linear sort of operation and then check large signal stability when maybe such significant perturbation as faults or phase jumps to be incorporated. And of course, if there are some challenges with the stability, further iteration with respect to the instability mitigation to be implemented. And at the end of the day, we believe that taking this approach would allow us to sort of have the system designed and ready for operation in a robust manner. Of course, one can see that there could be some discussions how to select, for instance, instability mitigation method. So this is a sort of work in progress that we will actually also look into this particular point, and also how to select and provide pass-fail criteria for small signal stability studies. Here we can just see an example of a system which sort of tried to define a benchmark system which is quite sort of representative for a converter-based power system. So meaning that with some grid forming, with some grid following converters, and also a representation of the grid with respect to resonant characteristics. And here one can see that from impedance-based stability analysis, we can easily see that the system can be unstable based on, for instance, Nyquist stability criteria. However, if there are some challenges with instability, then maybe more details like eigenvalue-based analysis to be investigated and check whether there are any, in this particular case, damping let's say eigenvalues with negative damping seen, and one can also determine it here when we can see the frequency, specific frequency for this particular eigenvalue, and also can be supported by participation factor analysis to define which state variables they contribute the most to the system. And of course, validation and further analysis in time domain is needed with the nonlinear system representation. I think for the last slide with respect to the content-related slide, I would like to bring also a little insight with respect to the model quality to be utilized in the studies. And of course, we also had work package 16 in within promotion, when there was quite a lot of focus on having the right methodology to derive and validate the models. So here I bring the example which is taken from IEC related to wind turbine model development and validation for harmonic studies, which is also relevant for stability studies, impedance-based stability studies, and we can see there are different classes when at early stage of the product development itself, the wind turbine development itself, the model can be derived based on simulated or calculated assumptions during the design phase. However, when sort of the product itself is more matured, then of course there's an opportunity to verify it in the lab by means of control hardware in the loop or even power hardware in the loop simulations. And at the end of the day, the most sort of mature verification, model verification approach would be to actually have some field measurements that would provide additional insight on the sort of subsystem converter behavior, and of course give more confidence in the models we use for the stability studies. At the end, I would like just to say that this is still work in progress. So even if we are about to finish very much soon work within promotion, there is still some work to be done also within SIGRE. And simultaneously, there are also a lot of other working groups that they sort of touch upon from different angle. Basically stability aspects, which we actually work on the same as in the work package 11 on harmonization, and we have continuous dialogue to assure that sort of the final outcome is aligned, so we don't provide any sort of contradictive statements or contradictive assumptions. So I think that is everything what I prepared for today. Thank you very much for your attention, and if we have Paul